Hey, everybody. So here we are again. We've got another rule. In the last video, we were looking at the product rule. What happens when we take the derivative of a function that is formed by taking the product of two functions? So it might make sense to ask ourselves what happens when we take the derivative of a function formed by taking the quotient. Oops. I said quotient, I made it a Q, which would be fine, but let's just go the traditional route. So here we have f and g are differentiable. And so we're taking their derivative. And just like with the product rule, right, it would be wonderful if we simply took the derivative of each and multiplied them together. But the product rule we saw was a bit more complicated. We wish we got the same kind of simplicity with the quotient rule, that we simply took the derivative of each and divided and took their quotient, right? That's how it works for limits. And we know derivatives are built by limits. But it turns out, because they're not just built by limits, there's a little extra thing going on there. It just doesn't work out that way. The way it does work out is that the derivative is we take the derivative of the numerator function and multiply it by the function in the denominator. Then we subtract the derivative of the denominator times the function in the numerator. And in the denominator, we get the original function, the same denominator function, but that function is now, we square the entire function. Okay, so it's a bit of a beast of a formula, but if we stay organized, we can get all the pieces in the right place. I'm going to skip the proof of this one. It's very similar to the proof of the product rule. You start with the definition, and you'll do this little trick of adding one again, adding zero. In the way I've done it, you're adding the product of f and g and the negative product of f and g, which comes out to zero. And with a little bit of manipulation, this formula pops out, right? We're not going to worry too much. I don't have a good sense of intuition around this. The proof is what it is, and it comes out with this formula, and we need to know how to apply it. So let's go ahead and do an example of applying this with the function k of x is equal to negative x to the fifth plus 1 over 2x plus 1. Let's try to find the tangent line to k of x at x equals 0. Okay, that's our job. So in order to do this, we need two things. We need a point and a slope. Let's do the easy part first. The point is just going to be the input 0. We need to know what the output. So to get the point, I'll simply compute k of 0, which is going to be 0 plus 1 over 0 plus 1, or just 1. So we get our point as 0, 1. Now, to get the slope, of course, we need the derivative. So the first thing we're going to do is compute the derivative. I'm going to do a little bit of work over here. The derivative of k of x. And the first thing I'm going to do, because this is an ugly formula and we're just getting started with it, I'm going to organize a little bit. I'm going to define two functions. The function in the numerator, I'm going to call f. The function in the denominator, I'm going to call g. This means that k of x is simply the quotient of these two functions. And so I know exactly how to take this derivative. I simply follow the quotient rule. Oops, should be g of x squared. Right? So I already know f and g right? And I know those functions. So what I need is the two derivatives. So I go back to my functions. I can apply the rules we learned a couple videos ago. So we've got our power rule and our constant multiplier rule. So the multiplier here is -1 times x to the 5th. So we pull that out front. Oh, and we're also using the sum rule. So I can take the derivative of -x to the 5th and 1 separately. And with that constant multiplier rule and the power rule, I get -5x to the 4th. The derivative of 1 of a constant function is 0. Similar process here, the derivative of 2x plus 1 is simply 2. The derivative of the constant goes away, the derivative of 2x is 2. And so now I have everything I need to write this function k prime of x. So f prime is -5x to the 4th times g minus g prime, which is 2, times f. -x to the 5th plus 1, all over g of x squared. And that's it. That's our derivative. Okay, not it for the whole problem, just this part of the problem. Now, we could simplify this, possibly expand things, collect like terms. It looks like we'll have a couple of x to the 5th terms, and then a couple other cross terms floating around out there. But since all I'm doing right now, I really wanted the derivative at 0, right? I need the slope at 0. So now I have a formula to plug 0 into. And when I plug 0 in, this is going to get really simple even without the simplification. So I'm not going to bother simplifying everything because we're simply going to compute k prime of 0. Well, this -5x to the 4th becomes a 0, which wipes out everything else. So we've got 0 minus 2 times 0 plus 1 is just 1. In the denominator, the 2x becomes 2 times 0 or 0, plus 1 squared is just 1. So this whole thing becomes -2. So we've now got the point 0, 1, the slope -2, and I can write the equation of this as y minus 1 equals -2x minus 0, or we could rearrange it, -2x plus 1. But either way, there is the slope of our tangent line using the quotient rule to get that slope. Let's, we haven't looked at a graph in a while. Let's take a look at a graph of this. So here is the graph of k of x, that -x to the 5th plus 1 over 2x plus 1. Notice it's got an asymptote at -1/2. And here's that tangent line, right? Hitting right at 0, 1. Notice this is a good example of where the tangent line can intersect more than one place. And notice also that as we zoom in, as we expect, this tangent line looks very similar to the graph, right? At this magnification, we can't see the difference, or we can just barely maybe make out a little edge of red up there. They're very similar at these points, right? This line and our function at that point and nearby are very similar. Of course, as soon as we zoom out, we see that they're very different kinds of functions. Okay. So that's the quotient rule. We'll do a lot more with the quotient rule as we gather other kinds of functions we can do. But notice this: we had polynomials already. Using the first set of rules that we developed, gave us the ability to do all polynomials. Now we're going to be able to do rational functions because they're the quotient of polynomials. And so as long as we can take the derivative of polynomials, the quotient rule lets us take the derivative then of their quotients. And so we can now add rational functions to the kinds of functions we can take derivatives of without having to go through this, the limit definition, right? This is what you would end up with if you did the limit definition. That is still true. We just have found a simpler way to do it. Even though this might be a bit complicated, it's still simpler than it would have been to try to do the limit as h goes to 0 of k of x plus h minus k of x over h, right? That would be a very complicated function. We'd have these quotients of negative x plus h to the fifth plus 1 times 2x plus h plus 1, right? It would just explode, sorry, divided by that, it would explode in complication. And now we get something that's, you know, a handful of lines here gives us the derivative. Another important consequence of this is we can now extend, remember we had the power rule, which said that if n is a positive integer, then the derivative of x to the n is nx to the n minus 1. With the quotient rule, we can get rid of the positive part if n is just an integer now, right? 0 works, but it's easier if we just throw 0 out, right? If 0 is the power on x, it's really just the constant function. We don't have to deal with what happens at 0, right? And make all these allowances for 0. So we're just going to say an integer, let's just say accept 0. It's easier that way, and just recognize that at 0, it's a constant. Let's prove this. Let's use the quotient rule to show this is true. Okay, so suppose n is a negative integer, right? So we already know this is true for the positive integers. Let's look at the negative integers. So n is a negative integer. Then let's take the derivative of x to the n is going to be equal to d dx of 1 over x to the negative n. Okay, so we've moved it into the denominator, right? This is one of our rules of exponents. And when we do that, we change signs, right? That's what the negative does there. Now, it's a little odd because n is negative, so negative n is now positive. We can use the quotient rule here. So let me rewrite the quotient rule where we can see it. I'll write it with a little shorthand. F derivative of f times g is f prime g minus g prime f all over g squared, okay? So now I'm going to treat the top function, the 1, as the function, I'll just write it, f of x equals 1, g of x equals x to the negative n. F prime is 0. G prime, now here's where it gets interesting, because x to the negative n is a negative integer. So negative n is a positive integer, which means I'm allowed to apply the power rule. We already know it works for positive integers. So the derivative of this, we take the exponent, which is a positive number, and we subtract 1 from that number. Okay, so there are the two derivatives we'll need to compute this derivative, because we're going to use the power rule. Tells me to take, if I'm calling the numerator f and the bottom, the denominator g, then I want to take f prime of x times g prime times g minus g prime of x times f all over g of x squared. So f prime we just discovered was 0, so it doesn't matter what g is. That first term is just a 0. G prime is negative n x to the negative n minus 1 times 1, so I don't need to write it. And in the denominator, we get g of x. Oops, let's write what g of x is. We get g of x, or x to the negative n squared. All right, let's do a little bit of simplifying. We got a negative and negative, so we'll have n x to the negative n minus 1. Rules of exponents, we simply multiply these two exponents together. So we have x to the negative 2n. Now I'm going to use one more rule of exponents. Since I'm dividing x by itself, but with exponents, I can subtract those exponents, right? So the n is just a constant out front, and we get x to the negative n minus 1. I'm subtracting negative 2n, so I'm adding 2n. Well, this gives me, I've got 2n minus n gives me an n, and I've got minus 1. And so the derivative x to the n is n times x to the n minus 1, which it always was when we had positive integers. Now we see that we can do that for all integers, negative integers as well. I wrote except 0. We just take the convention that if we have the function x to the 0, we usually just take the convention that at the input 0, it's still equal to 1, so we don't have these weird things. You would just never write it that way. So it's not a very consequential detail, right? If the function is constant, just write it as whatever constant that is. All right, so this is another big one, this extension of the power rule to all integer. Whoops, that was not a very straight line. Because now there's a whole new class of functions that we can take derivatives of. So for instance, if I want the derivative of, let's say, 1 over x, I could use the quotient rule, or I can simply write this as x to the negative 1 and use the power rule. Take the negative 1 out front, times x, and then subtract 1 from that exponent to the negative 2, and we get negative x to the negative 2. Right, so now these negative powers of x we can take derivatives of. Let's take a quick look at this graph and then do a couple more examples. So, all right, so here's 1 over x. Let's zoom in a little bit. Here's our derivative, negative x to the negative 2, right? So let's just remind ourselves what derivatives do. This green function is a function that spits out values of slopes of the tangent line. So let's go ahead and look at some tangent lines as well as the value of the derivative, which is going to be given by this green dot, right? So this green dot is going to travel along the derivative function. Its y value, the x value is the input, the x where we're looking, the y value is the y coordinate of that point, but it also tells us the slope of the tangent line to the red graph. The tangent line is also graphed here. It's a dotted red line. Maybe I'll change the color. Maybe it'll show up a little bit better. Let's make it black. There we go. So this black line is the tangent line. Let's add one more thing to this. All right, we're going to add a 1 divided by a. So we'll get the point where the tangent line is at. So now we've got 2 different points going on here, right? On the green graph, we're tracking the point, the x value that we're getting tangent lines at, and the green graph is spitting out the slope of those tangent lines. The blue point, or let's make it a red point, is traveling along the red graph, showing us where the tangent line is at, and then this dotted black line is the tangent line. So notice what happens. Right here, I'm starting at x equals -5. That red graph is very nearly flat. Right? You know this graph 1 over x is getting it's at an asymptote of the x-axis, so it's getting very flat there. And you see that the green graph is outputting -0.04, a small number because we have a flat graph. As I increase x, right? So you can see that there's not a lot of change, but that tangent line graph is slowly getting more negative. And you see the same thing happening to the green graph. So by here now, right, we went from -0.04 to -0.137. It's still a relatively flat line, but it's 4 times steeper or so than it was before, right? And you saw the slight shift in that tangent line. And then as we get close to that asymptote at 0, all of a sudden, the graph explodes downward. All right, so let's stop about here. At -3/10 about, right, we have the slope of the tangent line is -11. It's getting pretty steep. And what's going to happen as we go over this edge is it's only going to get steeper. And we see the green graph, right? It's not even on the screen anymore. This is an incredibly steep line. And then at 0, they both disappear. There's no values there. And then on the other side, we see our tangent line is still negatively sloped, right? The function 1 over x is now positive, and it's got really steep slopes in the negative direction. So the green graph, that little green dot's off the screen right now, but as I snake forward, we see this red graph getting flatter and flatter. So the values of the slope given by the green graph are getting closer and closer to 0, right? And I've gone out to 5 here, and we see it's the same value there, at least for the slope, whereas the actual value of the function is now on the positive side. All right, you know, there was a lot going on in that, but I just want to keep reminding us of this connection between these two functions, the derivative and the original function, right? That green graph here is spitting out values of the tangent line, slopes of the tangent line to the red graph. Okay, let's do just a couple more examples. Let's do one where we have to combine a couple of rules together. So let's look at 3x to the 4th. So I can think of this, I'm going to be really meticulous here. I can write this as 1/3 times x to the -4th, right? That's just rearranging that. We've got that x in the denominator. I brought up to the numerator. It's got x to the -4th. We've got a constant multiplier, so we can bring that out in front of the derivative, x to the -4th. The derivative, now we have our extended power rule, tells me to bring down. Oh, sorry, I made a mistake. That wasn't a 1/3. I don't know how I brought that to the denominator. I guess I was thinking about the x to the 4th, right? This is just a 3. It should be a 3 here as well. Same idea, it's constant, we can move it out front. And so now we have -4x, and we lower the exponent, so -4 minus 1 is -5, and then if we want to, we can combine, multiply those two constants out front, which we should. And there's our -12x to the -5th. That's the derivative of that function. All right, one more example to see that this new rule aligns well with our old rules. Let's do the derivative. What do I have? X squared plus 1. So we have a couple choices in how to do this. The first way in which I'm going to do it is I'm going to separate this fraction. Right, I'm not doing anything derivative yet. I'm just manipulating the function without changing it. Right, these are equivalent forms. X squared over x is going to be x plus 1 over x. Right. Now this is okay to do because x squared over x is not equal to x. It's not equal to x at everywhere but 0, because 0 over 0 is not defined, but x at 0 is defined to be 0. The reason I can get away with it here is I've also got a 1 over x. So the function that I have written, x plus 1 over x, isn't defined at 0 anyway. So the one place where this shouldn't be canceled is also a place that this function is not defined, so I'm not worried about that place. And so let's do one more manipulation. Let's rewrite this as x plus x to the -1. Now we can take our sum rule to do derivatives of each of these separately. The derivative of x is just 1. The derivative of x to the -1 is minus x to the -2, right? We take that -1 out front. You always write the 1, and then we lower the exponent by 1 unit. But we also could have done this using the quotient rule. We take the derivative of the top function, which is 2x, times the bottom function. Then we subtract the derivative of the bottom function, which is 1, times the numerator function. And all of this is over the bottom function, the denominator function squared. This looks very different than what I have written up there, but if we spend a minute, let's do a little bit of manipulation here. So 2x times x is 2x squared. Let's distribute that -1. We're going to get minus x squared minus 1 over x squared. 2x squared minus x squared is simply x squared. We've got a -1 over x squared. I can use rules of fractions, which is x squared over x squared is 1. 1 over x squared is x to the -2. Okay, same idea. I could cancel these x squareds because I don't have to worry about 0 because the other part of the function isn't defined at 0 anyhow. So I'm not worried about that point. But the bigger point is we got the same result, right? We're going to find that a lot with derivatives, that there's often many different paths we can take to the answer. You can decide for yourself, right? Unless someone's asking you to use a specific method, which one of these you like better. They're both equally valid. There's nothing wrong with deciding to use one or the other. If you can write your function as a quotient, you can use the quotient rule. If you can write it as a product, you can use the product rule. If you can write it as a power, you can use the power rule, and so on and so on and so on. Different ways that you write it can determine which way, what strategy you use to take the derivative. And as we get more strategies, we'll see that we have more choices opening up in a lot of cases. Okay, more on that later. That's it for the quotient function, quotient rule. Thanks, everybody. I will see you next time.